Our solar system is a vast and mysterious place. It's a cosmic ballet of planets, moons, and asteroids, all moving in a delicate dance around the sun. Among these celestial wonders, Saturn's moons stand out as particularly intriguing. Saturn, the ringed giant, has captivated astronomers for centuries. Its icy rings are a sight to behold, but the planet's moons are equally fascinating. These moons are not just chunks of rock and ice. They are dynamic worlds with active geology, hidden oceans, and the potential for life itself. Among Saturn's many moons, one stands out as particularly promising: Enceladus. This small, icy moon has captured the imagination of scientists and the public alike. Saturn, the sixth planet from our Sun, is a gas giant with a majestic system of rings. These rings, composed primarily of ice and rock, stretch thousands of kilometers wide, yet are remarkably thin. Orbiting this gas giant is a retinue of over 80 moons, each with its own unique characteristics. These moons range in size from tiny moonlets to Titan, a moon larger than the planet Mercury. But even among these fascinating moons, Enceladus shines brightly. Beneath its icy shell lies a hidden ocean, warmed by tidal forces from Saturn's powerful gravitational pull. It's a place where the ingredients for life as we know it, water, organic molecules, and a source of energy, may exist in abundance. Enceladus is a beacon of hope in our search for life beyond Earth. Enceladus, at first glance, might seem like an unremarkable icy world. Its surface, reflecting sunlight brilliantly, appears deceptively serene. But this small moon, only about 500 kilometers in diameter, holds a secret that has captivated scientists worldwide. Beneath its icy crust, hidden from view, lies a global ocean of liquid water. This ocean, kept warm by tidal forces exerted by Saturn and its other moons, is thought to be more voluminous than all the liquid water on Earth combined. From its south polar region, geysers erupt, spewing plumes of water vapor and ice particles into space. These geysers, originating from the moon's hidden ocean, provide us with a glimpse into its interior. Enceladus, a diamond in the rough, is a world that begs to be explored. Enter Cassini, our robotic emissary to the Saturnian system. Launched in 1997, the Cassini spacecraft spent 13 years exploring Saturn and its moons, revolutionizing our understanding of this distant world. Equipped with a suite of scientific instruments, Cassini acted as our eyes and ears, sending back a treasure trove of data and images. Among its many accomplishments, Cassini's observations of Enceladus stand out as truly groundbreaking. Before Cassini, Enceladus was thought to be a relatively inactive world, a frozen relic of the early solar system. But Cassini's close flybys revealed a much more dynamic and intriguing moon. The spacecraft detected plumes of water vapor and ice particles erupting from Enceladus's south polar region, hinting at a hidden ocean beneath the moon's icy shell. This discovery sent shockwaves through the scientific community, transforming Enceladus from an afterthought into a prime candidate for hosting life beyond Earth. Cassini had stumbled upon a mystery, and its subsequent observations would only deepen the intrigue surrounding this enigmatic moon. Cassini performed multiple close flybys of Enceladus, each time revealing new details about this enigmatic moon. The spacecraft's cameras captured stunning images of the moon's surface, revealing a complex landscape sculpted by ice tectonics and geyser activity. Long, linear features known as tiger stripes crisscrossed the south polar region, marking the source of the erupting plumes. Cassini's instruments detected organic molecules within these plumes, the building blocks of life as we know it. This discovery was a game changer, suggesting that the conditions necessary for life might exist within Enceladus's hidden ocean. Furthermore, Cassini's measurements of Enceladus's gravity field provided compelling evidence for a global subsurface ocean. This ocean, sandwiched between the moon's icy crust and rocky core, could be a haven for life, shielded from the harsh conditions of space. Cassini's flybys had transformed Enceladus from a cold, barren world into a top contender in the search for extraterrestrial life. The plumes erupting from Enceladus's south polar region are a sight to behold. Imagine jets of water vapor and ice particles, some reaching hundreds of kilometers in height, spewing out from cracks in the moon's icy surface. These plumes, backlit by the sun, create a stunning visual display, a testament to the dynamism of this tiny moon. But these plumes are more than just a cosmic spectacle. They are a window into Enceladus's interior, offering a glimpse of the hidden ocean that lies beneath. Cassini flew through these plumes on multiple occasions, using its instruments to analyze their composition. The spacecraft detected water vapor, ice particles, salts, and organic molecules, including methane, carbon dioxide, and simple organic compounds. These findings suggest that Enceladus's ocean is not just a stagnant pool of water, but a chemically rich environment with the potential for hydrothermal activity. How do we know about Enceladus's subsurface ocean if we've never actually seen it? The answer lies in a combination of observations and scientific deduction. Cassini's measurements of Enceladus's gravity field provided the first clue. The spacecraft detected slight variations in the moon's gravitational pull as it orbited Saturn. These variations could only be explained by the presence of a large, subsurface ocean denser than the icy crust above it. Furthermore, the composition of the plumes erupting from Enceladus's south polar region supports the existence of a subsurface ocean. The presence of salts, in particular, suggests that the plumes originate from a salty ocean in contact with the moon's rocky core. This interaction between water, rock, and heat could provide the chemical building blocks and energy sources necessary for life. The evidence is compelling. Enceladus harbors a hidden ocean, a place where the conditions for life as we know it may exist. Enceladus is a small moon, but it's caught in a gravitational tug-of-war. Saturn, with its immense gravity, exerts a powerful pull on Enceladus. This gravitational force isn't constant. It varies as Enceladus travels along its elliptical orbit. This variation in gravitational pull creates friction within Enceladus, generating heat. This tidal heating is what keeps Enceladus's subsurface ocean in a liquid state, even though the moon's surface is frozen solid. But tidal heating does more than just melt ice. It drives geological activity, creating the cracks and fissures in Enceladus's icy shell, from which the geysers erupt. This internal heat source is also thought to fuel hydrothermal vents on the moon's ocean floor. The plumes erupting from Enceladus aren't just water vapor and ice. They contain a complex mixture of chemicals, a chemical cocktail that hints at the conditions within the moon's hidden ocean. Cassini detected salts, suggesting a salty ocean, similar in salinity to Earth's oceans. This is important because it indicates that Enceladus's ocean is in contact with its rocky core, allowing for the exchange of minerals and chemicals. Even more intriguing was the detection of organic molecules, the building blocks of life. Cassini found methane, carbon dioxide, and simple organic compounds, suggesting that Enceladus's ocean is far from a sterile environment. These organic molecules could be the products of geological processes, or they could hint at the presence of biological activity. The presence of these chemicals, combined with the evidence for a subsurface ocean and hydrothermal vents, makes Enceladus one of the most promising places in our solar system to search for life beyond Earth. When we think about life beyond Earth, we often imagine creatures similar to those found on our own planet. But life, if it exists elsewhere, could take on forms vastly different from anything we can imagine. On Enceladus, with its subsurface ocean and lack of sunlight, life would have to adapt to extreme conditions. If life exists in Enceladus's ocean, it would likely be microbial, thriving in the darkness and relying on chemosynthesis rather than photosynthesis for energy. Chemosynthetic organisms, unlike plants, don't need sunlight to survive. Instead, they obtain energy from chemical reactions, such as those occurring near hydrothermal vents. The possibility of finding even microbial life on Enceladus would be a profound discovery, fundamentally changing our understanding of life in the universe. Enceladus has presented us with a tantalizing mystery, a moon with a hidden ocean, hydrothermal vents, and the potential for life. But to unravel this mystery, we need to go back. We need a dedicated mission to Enceladus, equipped with instruments capable of searching for signs of life. Imagine a future spacecraft, specifically designed to study Enceladus. It could fly through the moon's plumes, collecting samples for analysis. It could even carry a lander, capable of touching down on the surface and drilling through the ice to reach the ocean below. Such a mission would be a monumental undertaking, but the potential rewards are immense. Finding evidence of life on Enceladus would be one of the greatest scientific discoveries of all time, revolutionizing our understanding of our place in the universe. Saturn's moons are like a family portrait, each member with unique features and stories to tell. They range in size, composition, and temperament. Some are colossal, like Titan, shrouded in a thick atmosphere. Others are small and icy, like Enceladus, hiding secrets beneath their frozen shells. Imagine a celestial gathering. Titan, the eldest, commanding attention with its size and hazy atmosphere. Then there's Rhea and Dione, composed and traditional, primarily made of ice and rock. And then there's Enceladus, the smallest but perhaps the most intriguing, with its active geysers and hidden ocean. Each moon provides a unique piece of the puzzle, helping us understand the formation and evolution of planetary systems. Let's start with Titan, the largest of Saturn's moons, and a true giant in its own right. Imagine a world larger than the planet Mercury, cloaked in a thick, nitrogen-rich atmosphere that obscures its surface from view. This atmosphere is so dense that it creates its own weather patterns, complete with methane rain, rivers, and lakes. Titan is like a time capsule, preserving conditions that may have existed on early Earth. Its surface, shrouded in an orange haze, is thought to be composed of water ice and hydrocarbon lakes, creating a landscape unlike anything we've seen before. Beneath its thick atmosphere, Titan is thought to harbor a subsurface ocean of water and ammonia, potentially even larger than Enceladus's. This hidden ocean, along with Titan's complex chemistry and potential for organic molecules, makes it a prime target in the search for life beyond Earth. Rhea and Dione, two of Saturn's larger moons, are like celestial twins, composed primarily of ice and rock. They are heavily cratered, bearing the scars of billions of years of impacts, a testament to the tumultuous early solar system. These craters, some enormous in size, paint a picture of a violent past. a time when asteroids and comets roamed freely. Rhea, the larger of the two, is particularly intriguing. It's so large that it has its own faint ring system made up of dust and ice particles. Imagine a miniature version of Saturn's rings circling this icy moon. Dione, though smaller, is no less fascinating. It has a network of bright, wispy streaks on its surface, thought to be canyons formed by tectonic activity. These features suggest that Dione, though primarily composed of ice, may have experienced internal heating at some point in its history. Rhea and Dione, though often overshadowed by their more flamboyant siblings, offer valuable insights into the formation and evolution of icy moons. Their heavily cratered surfaces tell a story of ancient collisions, while their subtle features hint at a more dynamic past than meets the eye. Enceladus stands out as the rebellious younger sibling, full of surprises, spewing plumes of water vapor and ice particles from its south polar region. These geysers hint at Enceladus's internal heat and hidden ocean. Enceladus challenges our assumptions about where life might exist, offering a potential habitable environment in its subsurface ocean, a prime target in the search for life beyond Earth. Enceladus is a shining example of the unexpected wonders in our solar system. Before Enceladus, our search for life beyond Earth focused on planets more like our own. We looked for rocky planets with liquid water on their surfaces, orbiting within a star's habitable zone, like Goldilocks, searching for the perfect bowl of porridge. But Enceladus changed everything. Here was a moon, far from the sun's warmth, with a surface colder than ice, yet harboring a hidden ocean with the potential for life. Enceladus demonstrated that the habitable zone is not a rigid boundary, but a more fluid concept, expanding to include worlds with internal heat sources and subsurface oceans. This discovery was a game changer, expanding our understanding of where life might exist in the universe. It opened our eyes to the possibility of finding life in our own solar system, not on a distant planet, but on a moon orbiting Saturn. Enceladus became a beacon of hope, a testament to the resilience of life and its ability to find a foothold in the most unexpected of places. It forced us to rewrite our textbooks, to broaden our horizons, and to embrace the unknown in our quest for life beyond Earth. The discovery of Enceladus's hidden ocean and its potential for life forced scientists to rethink their assumptions about planetary habitability. Previously, the focus had been on finding planets within a star's habitable zone, where temperatures are just right for liquid water to exist on the surface. But Enceladus showed us that life could thrive even in the absence of sunlight, fueled by internal heat sources and chemical reactions. This expanded our understanding of the habitable zone, extending it to include worlds with subsurface oceans, warmed by tidal heating or radioactive decay rather than starlight. Suddenly, icy moons orbiting gas giants, once considered barren wastelands, became prime candidates in the search for extraterrestrial life. This shift in perspective was profound. It opened up a whole new realm of possibilities, suggesting that life might be far more common in the universe than we previously thought. No longer were we limited to searching for Earth-like planets orbiting sun-like stars. The universe, it seemed, was teeming with potential habitats, each with its own unique set of conditions that life could exploit. Enceladus not only expanded our definition of habitability, but it also provided tantalizing clues about the potential for life in its hidden ocean. The detection of organic molecules in the plumes erupting from its south polar region was a major breakthrough. These organic molecules, the building blocks of life as we know it, suggested that Enceladus's ocean is far from a sterile environment. It's a place where complex chemistry is taking place, driven by the interaction of water, rock, and heat. The presence of methane, in particular, was intriguing. On Earth, methane can be produced by both geological and biological processes. While it's possible that the methane on Enceladus is geological in origin, the possibility that it's a sign of microbial life is tantalizing. Furthermore, the presence of salts and other chemicals in the plumes suggests that Enceladus's ocean is in contact with its rocky core, allowing for the exchange of minerals and nutrients. This interaction between water and rock is crucial for life as we know it, providing the raw materials and energy sources necessary for life to emerge and thrive. The exploration of Enceladus has profound implications that extend far beyond our solar system. By studying this small, icy moon, we're learning about the potential for life throughout the universe. Enceladus has shown us that the ingredients for life are not unique to Earth. They can exist in the most unexpected places, even in the cold depths of our solar system. This realization has fueled our search for life beyond Earth. From the icy plains of Enceladus, we've glimpsed a universe brimming with possibilities. This small, Saturnian moon, once an afterthought in the grand scheme of space exploration, has emerged as a beacon of hope in our search for life beyond Earth. Who could have imagined that beneath its frigid exterior, a hidden ocean, warmer and potentially more voluminous than all of Earth's oceans combined, could exist? And yet, there it is, revealed through the tireless efforts of our robotic emissaries and the insatiable curiosity of the human spirit. The geysers erupting from Enceladus's south polar region, like cosmic smoke signals, hint at the dynamism hidden within this icy world. They speak of a place where water and rock interact, where organic molecules swirl, and where the potential for life, as we know it, or perhaps as we've never imagined it, beckons us forward. Enceladus has shattered our preconceived notions, expanded our understanding of where life might exist, and ignited our imaginations. It serves as a poignant reminder that the universe is full of surprises, waiting to be uncovered by those bold enough to seek them. The discoveries made by the Cassini mission at Enceladus were nothing short of revolutionary, but they were just the beginning. Like any good story, Cassini's exploration left us wanting more, hungry to delve deeper into the mysteries of this enigmatic moon. The next chapter in the Enceladus saga is already being written, with plans for future missions designed to pick up where Cassini left off. Imagine a spacecraft specifically designed to explore Enceladus, equipped with instruments capable of sniffing out the faintest traces of life. Picture it diving through the moon's plumes, collecting samples for analysis, and perhaps even landing on the surface to peer beneath the ice. Such a mission would be a testament to human ingenuity and our relentless pursuit of knowledge. It would allow us to study Enceladus's ocean in greater detail, to search for signs of hydrothermal activity, and to look for evidence of life itself. The answers to some of humanity's most profound questions. Are we alone? Is there life beyond Earth? May lie hidden beneath the icy shell of this small Saturnian moon. Enceladus has shown us that the ingredients for life are not unique to Earth. They may exist in abundance throughout our solar system and beyond, in the icy depths of distant moons and on planets orbiting other stars. Armed with this knowledge, we've embarked on a grand cosmic quest, a search for life beyond our pale blue dot. Telescopes, both on Earth and in space, are scanning the heavens, looking for signs of life on planets orbiting distant stars. And closer to home, missions are being planned to explore other potentially habitable worlds in our own solar system, such as Jupiter's moon Europa, which, like Enceladus, is thought to harbor a subsurface ocean. The search for life beyond Earth is a testament to the power of human curiosity, our innate desire to explore the unknown and to understand our place in the vast cosmic tapestry. It's a search that transcends borders and unites us in a common goal, reminding us that we are all part of something much larger than ourselves. The question of whether we are alone in the universe has captivated humanity for millennia. It's a question that has fueled countless myths, legends, and scientific inquiries. Discoveries at Enceladus suggest life beyond Earth is possible, even probable. The universe is vast, far beyond our ability to truly comprehend. Within its immensity, countless stars ignite, planets form, and perhaps life emerges. The possibility of other intelligent beings fills us with wonder and awe. We continue to explore, seeking answers to our most profound questions.